Hello everybody. Today is Wednesday, February 19th, and these are the solutions to your midterm review material. Let's just talk a little bit about what's going to be on the midterm before we start. The midterm is, by the way, on Thursday, February 27th. It will be written in class. The only exceptions would be those of you with accommodations. You will have already arranged an alternate day and time to write your midterm. The material that will be covered: the central limit theorem, the 3 t-tests, including confidence intervals for those tests, and then the only chi-squared model would be the goodness of fit test. What can you bring to the midterm? Bring a calculator. You will not be allowed to use cell phones, so you must have a calculator. And also you can bring a cheat sheet, 1 legal size paper. You can write anything you want on both sides of that paper. Okay, getting into it. And the first question, the purpose of this first question was to give you some practice in identifying which model is appropriate for the given scenario. So in the first case, we're talking about a company that makes shoes, and they found that 40% of the pairs sold in 2012 were black, 23% were white, and the remaining were of various other colors. When you see a statement like that, you should already be thinking goodness of fit test. Well, let's see. The CEO was curious to see whether the color preference has changed since 2012. And to do so, they plan to take a random sample of 120 pairs sold in 2024 to see if the proportions of each color are consistent with the data from 2012. So that is a goodness of fit test. We have one categorical variable, that's shoe color. We have one population from which we are drawing a random sample, and so that can only be a goodness of fit test. Next one, we have Kiboko and Sakwe. They're both chess players. Sakwe claims to be the stronger of the 2 players. That's a picture of Sakwe there on the left. To test this claim, Kiboko used a computer to evaluate her playing strength in each of 50 of her own games, and then selected 50 of Sakwe's games, and did the same thing, right? So you can see already we have 2 random samples: 50 games played by Kiboko, 50 games played by Sakwe. And so clearly this is going to be a 2-sample t-test because we have 2 samples. So we have one quantitative variable, that's the playing strength. And we have 2 populations. We're drawing samples from 2 populations, Kiboko's games versus Sakwe's games. So that must be a 2-sample t-test. Next one, so Ying asked 200 randomly selected students to tell her what their university major and their favorite sports are. She was interested to see whether statistics majors tend to prefer baseball more frequently compared to students with other majors. This one might be a little bit tricky. I think it should be pretty clear that we have 2 categorical variables. We have university major and favorite sports. So actually, once you know there's 2 categorical variables, it has to be an independence test. So notice the word independent or dependent doesn't appear in the scenario, but it should nevertheless be clear because the only chi-square test for which there are 2 categorical variables is the independence test. And by the way, you have to recognize that these are categorical variables. There's one population, which is the other condition for an independence test, and so that's what it is. Next one, Abdallah wanted to see whether drinking coffee improves cognitive skills. To find out, he asked 50 randomly selected students, none of whom had taken coffee, to complete a cognitive test. A week later, he asked the same students to complete a second cognitive test. So you should be able to recognize here that we're taking each one of our volunteers, our test subjects, and we're taking 2 measurements, one when they didn't drink coffee and one when they did. And so that can only be a paired t-test. So we have one quantitative variable, it's cognitive test scores before and after. So we have 2 measurements on each individual, and it's one population from which we draw a random sample. And so that's a paired t-test. Next one, after visiting the Netherlands, Charvi told her friend Manpreet that adults in that country are very tall. It suggested that their average height is more than 6 feet. Manpreet decided to test this claim by collecting the heights of 200 randomly selected Dutch adults. So here our variable is height in feet. That's a quantitative variable. We're drawing a sample from one population, so this can only be a one sample t-test. Number 6, Canadians have several ways to get to work. They can drive, they can bus, they can cycle, they can walk. In a recent survey, 300 randomly selected adults living in 5 large Canadian cities were asked which option they chose most frequently. The investigator plans to see whether the distribution of choices is the same for all 5 cities. So what do we have here? We have one categorical variable. That's the method of transportation. And we're drawing samples from 5 Canadian cities, and so we have 5 populations. So the only chi-squared model that has more than one population is the homogeneity test. And so this must be a homogeneity test. Right, so there they are. So you can check to see if your answers were the same as these answers. Okay, question 2. In 2023, Patty spent 2.3 hours per day on average playing computer games. Patty's parents asked her to play less. So what are they going to do? They're going to set up a device on her computer to keep track of how much time per day Patty is playing her computer games. And just to make it clear that we can use the model that we're about to use, let's say that the device collects recordings at random, so it represents a random sample. So here we have a random sample of 25 recordings, and we have an average of 1.8 hours per day, and we have a standard deviation of 0.35 hours per day. So the question is, does this data provide evidence that Patty's average playing time is now less than 2.3 hours per day? So there's our data: sample size, sample mean, sample standard deviation. It should be clear that this is a one sample t-test. The null hypothesis would be that Patty's playing time is still 2.3 hours per day, and the alternative would be that it's less than that. And note too that this symbol mu represents Patty's population mean playing time per day. That is the parameter of interest for which we need to make an inference. So the first part of this question, given the sample size, what must be assumed in this scenario? So the sample size was only 25. And so because of that, we must assume that the distribution of Patty's playing time per day is either approximately normal, or if it is skewed, then the tails of the distribution are not heavy. So we can suppose that this is the case, provided there are no extreme outliers in those 25 data points. So if we actually had the data, we could make a box and whisker plot, and that would tell us whether or not there's outliers, extreme outliers. And so what am I appealing to provide this answer? I'm appealing to those conditions where if the underlying distribution for individual measurements is not normal, then we have our 3 cases. And our sample size condition depends on how normal or how unnormal the distribution for individual measurements is. And so the one we're using here is the one in the middle. We have a sample size of 25, and so at the worst, the distribution for individual measurements would be skewed, but with no extreme outliers. Next, what are the hypotheses in this scenario? I guess we already looked at those. And that is either her playing time is still 2.3 hours per day, or it's something less. Next, what is the critical value for a 1% test? So I don't remember if I said in the original scenario that we're going to conduct a 1% test. But here the question is specifying 1%. So the degrees of freedom. Data size is 25. We have 25 measurements. The degrees of freedom is 1 less, 24. So we can get actually an exact critical value this time. We're looking at a one-tail test, so we're looking at a one-tail probability. That one-tail probability needs to be 1%, and so our critical value is 2.492. So it's a lower tail test. This is our critical value, right? So, right, here's the point I wanted to make. We're conducting a lower tail test, and remember the t-table only gives values for the upper tail, the positive values. And so how do you get the value, the critical value for a lower tail test? You just put a negative sign in front of it. So we got that in here. This gives us a decision rule. We will reject a null hypothesis if our test statistic is less than minus 2.492. Next, we're going to compute the test statistic and what can you conclude. So I see I have the conclusion already displayed here. Well, let's see how come I came to that conclusion. Oh, there it is. So the test statistic is the difference between what we observed, 1.8 hours per day, and what we would expect to see if the null hypothesis was true, 2.3. And then we divide by our measure of uncertainty. That would be the standard error of y bar. So doing that calculation, we can see we get a test statistic that is way, way to the left. And clearly then, there's very strong evidence, in fact, to reject the null. The evidence against the null is very strong. The evidence in favor of the alternative is very strong. And how strong is the evidence? We want to get an approximate p-value. And we can see that if our test statistic was 2.797 minus, then the area in that lower tail would be 0.005. Our test statistic is way further away to the left, and so our p-value is much smaller than 0.005. And so the evidence against the null hypothesis and in favor of the alternative is very strong. What's this? Right, so I remember now. I was going to give one quick slide just to review once more the whole meaning of a p-value. So if this on the right here is it's a sketch of the distribution of our test statistic. It was a t distribution with 24 degrees of freedom. And so here is our test statistic. And what is the p-value? The p-value is the area in that lower tail to the left of our test statistic. So it's the area down in that lower tail. And so just to review this concept, the p-value is the area to the left of our test statistic. What does it really mean? It is the probability that a test statistic would be further to the left than the value we observed if the experiment was repeated, assuming the null hypothesis is true. Okay, question 3. The playing strength of 60 randomly selected chess players was assessed. The students then attended a 1-week chess camp in which they participated in a variety of chess learning activities. Their playing strengths were then reassessed. Right, so this looks like a before and after scenario. It's going to be a paired t-test. And so we have a mean change in playing strength, 115.9 rating points, and a standard deviation of 73.6. Right, so is there sufficient evidence to conclude that attending chess camp will improve playing strength on average? Right, so here's our data. And the parameter of interest, mu sub d, it's a difference. So this is the population mean difference in playing strength after attending chess camp minus before. So in this case, we're not going to conduct a hypothesis test, but instead we're just going to construct a 95% confidence interval. So we need a critical value. Just going back again and remind myself, what is the data size? Okay, we have 60 data points. So the degrees of freedom is 59. And the best we can do as an approximation using the t-table is to look at degrees of freedom 50. And so for a 95% interval, the critical value is 2.009. So here's our data. Again, the parameter of interest is the population mean difference in playing strength after minus before, after attending chess camp minus before. And the reason I'm putting this there is because in a minute we're going to need to interpret our confidence interval, and knowing what the parameter of interest is can help you do that. So the confidence interval itself is pretty straightforward to calculate. We have a point estimate plus or minus a margin of error. The margin of error has two parts. It's going to have a critical value, that's the t-value, times a standard error. The standard error we can calculate right now. It's just going to be the standard deviation from the sample divided by the square root of the sample size. And so plugging those in, we get an upper and lower bound for our 95% confidence interval. So, how do we interpret this interval? Assuming the conditions for the central limit theorem are satisfied, we are 95% confident that the population mean difference in playing strength after chess camp minus before chess camp is between these numbers, 96.81 and 134.99 points. Since 0 is not in this interval, we have evidence that attending chess camp makes a difference. Moreover, since the interval is positive, we can conclude at the 95% level of confidence that attending chess camp improves chess playing strength on average. Next one. Adults vary in height between populations. Adults in the Netherlands, for example, tend to be quite tall, whereas adults in the Philippines tend to be comparatively short. So the following Minitab output shows an analysis for 45 randomly selected adult males from the Netherlands and 38 adult males randomly selected from the Philippines. So you can see here we have two random samples, and it's quantitative data. This can only be a two-sample t-test, which you can see from the Minitab output. So the first question is to calculate the standard error for the difference between the sample means. This is the most complicated calculation that you will see on the midterm and on the final as well. Actually, for most of this course, the calculations are much more straightforward. This one is a bit complicated because, well, it's tedious. That's really what it is. It's tedious because you have to use this kind of ugly formula. So the trick here is to know exactly what numbers go where, and then how to use your calculator in an efficient way to compute the result. So here, I'll just show you how the numbers are plugged in. So you can check, let's see, so where do we get these? The numbers on top of each fraction come from the standard deviation. So you can see in the descriptive statistics where the sample standard deviations are. And of course, those numbers need to be squared. The numbers on the bottom of each fraction come from the column called n, which means sample size. And so we can calculate each of these fractions, add them together, and take a square root. We get a standard error of 4.2850. Okay, whatever. So what are we going to do with this? We're going to construct a 99% confidence interval for the difference between the population means. And then we'll provide an interpretation. So let's see. Why am I pulling this up again? Don't remember. Oh, I do remember. Right, I do remember. This is a two-sample t-test. And so you must be given the degrees of freedom. There's no way you can figure that out on your own because we didn't show you how to do that. It's a difficult calculation. But look at the table on the right for the test. DF is the degrees of freedom. So the degrees of freedom is given. It's not given in this scenario. You have to know how to find that degrees of freedom from the Minitab output, and there it is. So we have 80 degrees of freedom. So we go to our t-table, 80 degrees of freedom. We don't have 80 on the t-table, so the best we can do is to approximate with 75 degrees of freedom. It was to be a 99% interval, and so the critical value is 2.643. And so now we can go ahead and perform our calculation. So as all confidence intervals are constructed, we start with a point estimate. In this case, the point estimate is the difference between sample means, plus or minus a margin of error. The margin of error has a t-value, critical value from the table, and it has the standard error of the point estimate. So we have all of these numbers now. You can see from the descriptive statistics, we get y1 bar and we have y2 bar. So we can take that difference. We have our critical value and we have our standard error. And so we just do that calculation. We get our upper and lower bounds. So how do we do this interpretation? Assuming the conditions for the central limit theorem are satisfied, we are 99% confident that the difference between the population mean heights is between 10.67 centimeters and 33.33 centimeters. I see I wrote here centimeter points. Let me just take that out. That was a bit careless. Since 0 is not in this interval, we have evidence that there is a difference in the population mean heights, and since the interval is positive, we can conclude at the 99% level of confidence that adults from the Netherlands are taller on average compared to adults in the Philippines. Okay, the next question is the test statistic for the null hypothesis versus the two-tailed alternative is provided in the table, and you're to show how this test statistic was calculated. I said the table below, right? So anyway, you've seen the table. If we just go back to that for a minute. Right, you can see the test statistic is here. It's the t-value. And we're going to show how that test statistic is calculated. Right, so that's pretty straightforward. Test statistics, t-statistics are always calculated in the same way. You start with what you observed. In this case, it's the difference between means, minus what you would expect to see if the null was true, divided by a measure of uncertainty. Now just notice that I have the y1s and y2s mixed up. So let's just be clear. The first sample consists of what? The first sample would be adults from the Netherlands. The second sample is adults from the Philippines. And we're taking y1 minus y2. So I just noticed that I have these backwards. So let me just correct that. And it doesn't make a difference in the expression below for the measure of uncertainty. It doesn't really make a difference because we're adding them. But just to be perfectly clear, I will fix that as well. 2 and 2. Right. Right, so the point of this is in the past I've seen cases on midterms and finals where they do give you tables where you have values like t-statistics and p-values already calculated, and you might be asked to show how they are calculated. And the nice thing about these kinds of questions is you know when you got it wrong, right? So if we did this calculation and our calculated t-value was not 5.13, then we would know we did something wrong and we could correct ourselves. So that makes it more likely you're going to get this question right. Anyway, let me just continue. Let's see, what's the last part? The test statistic for the null hypothesis versus the two-tailed alternative is provided. Show how this was calculated. Did I accidentally have this slide here twice? Yeah, I did. Yeah, I need to take that one out. Yeah. Sorry guys. Up all night again. So I'm not my brain is not working as well as usual, and even it usually doesn't work that well in the first place. So I'm sure you'll be patient with me. Let me just continue. Okay. I guess we're on to the next question already, yes? Yes, okay, good. Question 5. Okay, sales data for all handbags sold in Canada indicates that 50% are black, 30% are brown, 10% are white, 5% are red, 5% are some other color. So when you see percentages like this, you should be starting to think, this looks like a goodness of fit test. Let's continue. A random sample of 200 handbags sold by the Handy Handbag Company was collected. And then we're given a table. And so from the table itself, you can tell for sure this is a goodness of fit test. And how do we know? Because this is a frequency table. If you look at the first two columns, we have our categories. There's one categorical variable, by the way. And we have our observed count. So those two columns together consist of a frequency table. And so that tells us that we must be doing a goodness of fit test, because the other chi-squared tests, the homogeneity test and the independence test, the data comes in a contingency table, not a frequency table, right? So, okay, so what are we being asked here? Explain why all the conditions required to perform a goodness of fit test are satisfied in this scenario. Well, let's just review those conditions. We need to be sure there's one categorical variable, a sample from one population. It has to be a random sample, and that's supposed to give us independence. And then all expected counts are 5 or more. So there, in this case, there is one categorical variable. It's handbag color. And it's a sample drawn from one population. That's the population itself is all handbags made by the Handy Handbag Company. The sample is random, and so we can assume independence. And the smallest expected count is 10, and so the expected counts condition is satisfied. So we are all good. Just going back for a moment. Right, so you can see that in the column labeled expected, these are the expected values. Assuming the null hypothesis is true, you can see all of those are 5 or more, so we're good. Okay, next one. Okay, state the null and alternative hypotheses. So here, we could say it in words. Probably that's the easiest way to do it. The null hypothesis is that the population proportion of handbags of each color sold by the Handy Handbag Company is the same as the population proportions for all handbags sold in Canada. So see those test proportions? Those would come from the percentages that were given in this scenario. That represents the distribution of these probabilities or proportions for handbags sold in all of Canada. So the null hypothesis is that for the Handy Handbag Company, their population proportions are equal to those test proportions. Another way of saying it is that the null is that the observed counts are consistent with the test proportions. Right, what's the alternative? That's just that there are differences between these two population distributions. So in other words, it's not the null hypothesis. Oh, yeah, I forgot I was going to do that. What's the critical value for a 5% test? You need to remember that if you're conducting a goodness of fit test, the degrees of freedom is the number of categories minus 1. So here we have 5 color categories. 5 minus 1 is 4 degrees of freedom. We go to the table, looking at 4 degrees of freedom. If it's a 5% test, our critical value is 9.488. And so our decision rule is we will reject the null hypothesis at the 5% level of significance if the test statistic is greater than this critical value. Here we're going to calculate the test statistic. How do we do that? Well, we already have our expectations, so we don't need to calculate those. And we already have our contribution to the chi-squared statistics. We don't have to calculate those either. All we really need to do is to add up those contributions. So if we add those up, we get our test statistic, our chi-squared test statistic being 29.1568. A very big value, by the way. And so we can reject the null and conclude that the color distribution of handbags sold by the Handy Handbag Company is different than the color distribution of handbags sold in Canada. Which category? Oh boy, here's another. I see on the bottom. I left that in. I meant to animate that. Anyway, which color category is least consistent with the null hypothesis, and explain your choice? Well, remember that when you're conducting these chi-squared tests, what you're measuring with the chi-squared statistic is the statistical distance between what you observed and what you would expect to see if the null was true. So it's the distance between the column called observed and the column called expected. And if you look at those chi-squared contributions, the category that made the biggest contribution would be red handbags. And so the observed value, you can see the handy handbag company in this sample size of, I don't remember the sample size. What was it, 200? Let me check. Good grief. Oh, I don't know. I have to add those numbers together. I don't even know the sample size. Anyway, so if you add these numbers together, these observations, you get a sample size. Let's just find out what the sample size is. Cheapers. I'm sorry this video is so tedious, but anyways, what can you do? It is 200. Yeah, it's 200. Maybe it said 200. I don't remember. Okay, so the sample size is 200. Now here's the point. What's going on with the red handbags? We can see that the contribution to the chi-squared statistic for that category is the biggest of all of them. And if we look at the observations in a sample size of 200, we saw 21 of those bags were red. But if the null is true, we would expect to see on average only 10. And so you can see what we observed is quite a bit larger. And so it appears that of the handbags sold by this handy handbag company, they're selling more red ones than what you would expect to see if the null was true. Right, so the color category red is the least consistent with the null. This observation, 21, has the largest deviance and therefore makes the largest contribution to the chi-squared statistic that measures the statistical distance between observed and expected counts. Okay, that could have been easier. Let's see. Okay, we have two more questions. These last two questions cover, let's see, the first one looks like a homogeneity test, and the question 7 would be an independence test. Just to be clear, on the midterm, you will only be seeing, amongst the chi-squared tests, you will only be seeing the goodness of fit test. However, I'm going to continue going through these because some of you probably solve these ones anyway, and these are certainly the kinds of questions you will see on the final exam. So let's go through these. So here, data was collected from 3 Tim Hortons locations. We have our data table here: Halifax, Vancouver, and Iqaluit, and we're looking at the distribution of the size of coffee cups sold at a local Tim Hortons. So we have 3 size categories, and we have 3 populations from which we're drawing. This is a homogeneity test. And the first question was to fill in the missing values. And so before we do that, let's just talk about what must be assumed, right, to conduct a homogeneity test. We must have one categorical variable and samples drawn from 2 or more populations. In this case, we have samples from 3 populations. It's got to be a random sample. That gives us independence within samples. And all expected counts must be 5 or more. So to check this 5 or more condition, we need to fill in those empty spaces on the table. We'll do that in a moment. State the null and alternative hypothesis for a homogeneity test. The null hypothesis is that the population proportions for the sizes of coffee cups sold, small, medium, large, is the same at all 3 locations. The alternative hypothesis is that the population proportions are different for at least one of those locations. And now what do we have here? Oh, something weird going on. Let's go through these. So the thing you need to remember when you're faced with a contingency table, and this could be for a homogeneity test, like we're seeing here, or an independence test. You need to realize that the way the data is displayed in Minitab and as it will be presented to you on the final exam, we have for each contingency, we have 3 numbers. The first number is the observed count. The second number is the expected count, assuming the null is true. The third number would be the chi-squared contribution. So for part A, we're looking at the number in the middle. That's an expectation. To get the expectation, you take the column total divided by the grand total times the row total. Oops, I didn't mean to do that. And so we get that number, 24.9774. For part B, we're looking at the third number. So that's a chi-squared contribution To do that calculation, we take what we observed, 187, minus what we expected, 181.7. So that's our deviance. We square the deviance, and then we divide again by the expectation. So that contribution is, in this case, 0.1546. For part C, here we're looking at an observed count. So to get the observed count, we notice that if we go across those counts for Vancouver, the sample size is 883. So if we subtract 52 and subtract 348, what's left over will be the counts under that box C. So that's going to be 483. Part D, again, we're looking at a chi-squared contribution, and so we take what was observed, 11, minus what we would expect to see if the null was true, 12.5. Squaring that deviance, dividing again by expectation, we get 0.18. And finally, for part E, here it's the number in the middle. This is an expectation again. And so we take the column total, that's 663, divided by the grand total, 1550, and then multiply by the row total, 222. We get 90.6619. Okay, so next, what is the critical value for a 5% test? First, we need degrees of freedom. In any case where you're given a contingency table, the degrees of freedom is the number of rows minus 1 times the number of columns minus 1. Now, just to be clear, looking at this table, when we count rows and columns, we do not include the margins. And so here we have 3 rows and 3 columns. And so 3 minus 1 times 3 minus 1 gives us 4 degrees of freedom. We're looking for a 5% test. And so the critical value is, again, 9.488. Our decision rule will be that we will reject the null hypothesis at the 5% level of significance if the test statistic is bigger than this critical value. Next, we're going to calculate the test statistic. Right, so how do we do that? Well, we just have to add up all the chi-squared contributions. Now, I hasten to add that on a midterm or final, you're not going to be expected to add up a whole bunch of numbers like this. But I made you do this for the review, just to emphasize that to get the chi-squared statistic, that's all you need to do in the end, is add up all these contributions. So here we can see our test statistic. Where is it? It's here. Our test statistic is very small. It's smaller than the critical value, so we therefore conclude that there is insufficient evidence to reject the null hypothesis at the 5% level of significance. Great, so that brings us to the last question. So here, using a stratified sampling, using stratified sampling, 100 randomly selected people between 20 to 30 years of age, 100 between 31 and 40, and 100 between 41 and 50, were asked how they get to work. All 300 people live within a 20-kilometer radius of downtown Toronto. Excuse me. And so have access to the same infrastructure. Using this mini-tab I'll provided, determine whether there's evidence that the means a person uses to commute to work depends on their age category. So this one should be fairly straightforward. Let's see. First, what kind of test is this, you might ask yourself. We have 2 categorical variables. We have the age of a person and the means by which they go to work. And we have a sample from one population. It's true that it's a stratified sample, but don't be fooled. It's still just one sample from one population. So we have one population, we have 2 categorical variables. The only test for which there are more than one categorical variables would be the independence test. So we know this must be an independence test. Also, of course, the question asks whether the means of transportation depends on the age category. So the word depends is actually in this scenario. And so that's how come we know it's a chi-squared independence test. Notice that we're not given a level of significance. So we cannot ever reject or not reject the null hypothesis. What we can do is calculate the test statistic and then a p-value to assess the strength of the evidence against the null hypothesis. That being that age category and the means of transportation are independent. Right, so we can get the weight of the evidence, the strength of the evidence against the null, or equivalently, we could say the strength of the evidence in favor of the alternative. So how do we do that? Again, we just have to add up all those numbers. It's a bit tedious, but not difficult. This is your chi-square test statistic. And if you look at output from Minitab, you can see the same test statistic. So if this was a midterm or final, you wouldn't have to do the calculation of the chi-squared. You would have to only to be able to identify the chi-squared statistic from the Minitab output, as you see in the table here. And so it's the Pearson chi-squared statistic, not the likelihood ratio value. So we need to take that number. We don't have a level of significance, so we cannot compare this number with a critical value. But what we can do is approximate the p-value. So the degrees of freedom, it's the number of rows minus 1 times the number of columns minus 1. And just once more, when we count rows and columns, we do not count the margins. So here we have 3 rows and we have 4 columns. And so that gives us 6 degrees of freedom. And our test statistic, oh, what was it again? I forget already. It was 15 point something, 15.772. So our test statistic is between these two numbers, which means our p-value is between the corresponding probabilities. Sorry about that. Our test statistic is between 14.449 and 16.812, and so the p-value for the test is therefore more than 1%, but less than 2.5%. And so now we can use this p-value to say something about the strength of the evidence against the null hypothesis, or equivalently in favor of the alternative. So here the p-value for the test is more than 1%, less than 2.5%. We can therefore say that the evidence against the null hypothesis, or in favor of the alternative, is moderate. And why do I say moderate? Because of this table. We're in this interval. Wow, I think that's it. I got through it. Guys, it's time for me to take a nap. If you have any questions about this, if anything was unclear, you can leave a comment on the YouTube channel. I'll check for those. Or you can send me an email, or you can wait until I see you next week. There will be time to answer a few questions next week because, remember, the midterm isn't until Thursday. I will see you on Tuesday. Tuesday next week. Study well. I'll see you next week. Bye-bye.